Hi, my name is Amir Carmel. I'm Michal's student, and I will talk about algorithm for maximum parsimony, which is a model for phylogenetic reconstruction. This is a joint work. Again, my name is Amir Carmel, Noah Lempel, Dekel Tzu, and Michal. So what's phylogeny? You've probably seen this before. So formally, it's a graph-like structure whose topology describes the inferred evolutionary history among a set of species. Phylogenies are modeled as either rooted or unrooted, labeled binary trees, and the input entities are assigned to the leaf. So as you can see here, this is the input. So in maximum parsimony is a character-based method. Each species is characterized by a sequence of letters. We are given a substitution scoring matrix for the scores, and our goal is to find topology and assignment for the internal vertices. Okay, rooted phylogenies. So what is the difference between rooted phylogeny and unrooted phylogeny? So this is an example for unrooted phylogeny and rooted phylogeny. So the decision whether to model phylogenies as rooted versus unrooted depends on the substitution scoring matrix. In order to model phylogenies as unrooted topology, with unrooted topology, you need the assumption of symmetric scoring matrices. If the matrix is asymmetric, you must model with rooted phylogenies. Today, many applications assume asymmetric scoring matrices, which gives motivation for the use of algorithm for reconstruction of rooted phylogenies. So the Parsimony Maximization model is a classical model for phylogenetic reconstruction. In this model, we want to find the tree topologies that seeks the least amount of evolutionary changes over the tree. There are two problems inferred from this model, the small parsimony model and the large, which calls also the maximum parsimony model problem. We'll start with the small parsimony problem. In this problem, the input is the multiple alignment and the tree topology over n leaves. And our goal in this problem is to find just the assignment for the internal vertices that will minimize the scoring function. So again, there is always a substitution scoring matrix or a scoring function in the background. So here we have, in this example, we assume Hamming distance. So you know Hamming distance. So in the left, there is one mutation from C to G, and in the right we have two mutations, and therefore the score here is 1 and the score here is 2. So we want with the minimal number of mutations, and this is what we want to find. We note that non-algorithm for small parsimony traverse the tree in a bottom-up manner, from the leaves up to the root. So in this example, this is only for the second column, and this is again in each node we have the entire assignment for. So this is, we denote by n the number of species, and by m the length of the sequences. In the maximum parsimony problem, the input is just the multiple alignment, and we want to find topology and assignment for the internal vertices of this topology that will minimize the small parsimony score. So again, here the search space is much, much bigger over all phylogenies and over all assignments. So this is the two previous topology and assignment and the new different topology. And this problem is known to be NP-hard. So in this work, we'll measure the algorithm in terms of assignment operations. Assignment operation is the time to compute the assignment for a single vertex in the topology, and this depends on the scoring we define. So if we use Hamming distance scores, then we can use features algorithm, which give us O of m times for finding the assignment for a single vertex. And using weighted eddy distance, Sanchez algorithm gives m times sigma square. So now, if you will see the running time complexity, we won't have this m factor, because it will be hidden in this assignment operation. So now I'll talk about our contribution, starting with previous result. So the first is of Cavalli-Sforza and Edward. Cavalli-Sforza and Edward surveys different models for parsimony maximization. For phylogenetic reconstruction, one of them is the parsimony model, and in their approach they have n-1 times 2n minus 3 double factorial assignment operation, where 2n minus 3 double factorial is the product of all odd numbers, up to 2n minus 3. Later, Hendy and Penny gave a different approach, which is a branch and bound algorithm. They did not properly analyze its worst-case running time. This was our first contribution, was to give an exact worst-case running time for Hendy and Penny algorithm, which is actually faster than the one of Cavalli-Sforza and Edwards, and it's square root of n times 2n minus 3 double factorial. And we also proposed a new faster algorithm, which executes theta of 2n minus 3 double factorial assignment operations. So now surveys this algorithm, starting with the one of Cavalli-Sforza and Edwards, which is very basic. So again, I'll talk about their contributions. They surveyed different models for phylogenetic reconstruction. They counted also the number of rooted phylogenies and showed that this is the 2n minus 3 double factorial. So in their algorithms, in their approach, they enumerate all phylogenies in some manner, and they execute the small parsimony algorithm on each topology. So each topology has n minus 1 internal vertices, and therefore the running time is n minus 1 times the number of phylogenies, assignment operations. Okay, now I'm getting to the Hendy and Penny algorithm. So in Hendy and Penny algorithm, as you can see, there is some search space. So they traverse they enumerate the phylogenies on the search space. In each node, we have another tree. This tree is the phylogenies. So again, the internal node has the phylogeny, and the external node is the search space tree. And in level I of the search space tree, we have all phylogenies with I leaves. So how can we obtain a new node from its parent? So for each edge in the node, we break the edge, we add the new internal vertex, and connect it to the new leaf. This is how we expand the search space tree. And now, Hendy and Penny, what they did is they interleave the small parsimony algorithm within the search space traversal. So now we need to recalculate the assignment for this node. So this is one assignment operation. And now we need to recalculate this node because it now has a different child. So we have two assignment operations here. So another for a different edge, we break the edge, add internal vertex, connect it to the new leaf, and then we need to go all the way up to the root and update the assignments. So this node has 4 edges, as you can see, and therefore there's 4 children, and the 5th child will be obtained from adding a new root and connecting it to the new leaf and to the parent phylogeny. So overall, this is the number of assignment operations in this example. So we have 1, then 5, and then it goes a lot more. This is only one node, so it's not so sure how it grows. And also we note that the small parsimony calculations are in a bottom-up, while the search-based development, the phylogenies, are built in a top-down order. So this is one thing that we note. So now we also, as I said, our first contribution was to calculate the exact worst-case running time. So as you can see, it's equals to the number of assignment operations. So this is what we will count now. So again, I'll say that they proposed this algorithm for the purpose of branch and bound, and they did not properly analyze its worst-case running time. So we denote by num_unc the number of ancestors for a node V in the search space tree, which is a phylogeny. So the number of assignment operations is this is the number of ancestors, the nodes that are gray. So we'll count the number of assignment operations. This is equal to the number of ancestors for in node V. And we'll denote by HI, which will be more convenient, the sum of all num_unc for all nodes in level I in the search space tree, in level I plus 1. And by this definition, this equality holds. So our purpose now is to sum over num_unc for this entire search space tree, which is equal to the sum of HI. In M11, we show that HI is equal to 2i double factorial minus 2i minus 1 double factorial, and which leads to theorem 2, where we show that the worst-case running time of Hendy and Penny is equal to square root of n times 2n minus 3 double factorial. So this is a lot of combinatorial work that we are doing here. And now we are getting to our algorithm. Our algorithm has a more efficient search space tree. So we will build the search space tree in a bottom-up order. So we'll get a new node from its parent by merging any two subtrees. So here we merge 1 and 2, 1 and 3, and 3 and 4. So in the first level, we'll have n choose 2 children. And again, we interleave the small parsimony algorithm within the search space traversal. So there is one assignment operation per node. Okay, so another level maybe. We merge with 3, we merge with 4, and then we merge 3 and 4. And in the other direction, we merge 1 and 2. So here we have our first challenge. So we can get the same node from two different sequences of merge operations. So in this example, we merge 1 and 2 and then 3 and 4. In the other direction, we merge 3 and 4 and then 1 and 2. So this is not a tree yet. This is just what we call a search space graph. We'll show a canonical representation for the search space tree nodes to get this, to make it a tree actually. So again, this is how the tree looks like. So again, in the last level, we have all phylogenies over n leaves, and we are doing one assignment operation per node. So we need to count the number of nodes in this search space tree in order to get the worst case running time. So again, our new algorithm develops the search space tree in a bottom-up order, which follows along with the natural bottom-up order of small parsimony. We first define the graph Gn, and then I will show a canonical representation for making this graph into a tree by removing those redundant edges. Using combinatorial analysis, we showed that the size of the graph is approximately E times the number of phylogenies. E is the base of the natural logarithm. And lastly, we show that, well, again, traversing the search space tree requires performing exactly one assignment operation per node, and therefore the algorithm running time is approximately the number of phylogenies, in the same order of the number of phylogenies. Okay, so now I'll talk about the canonical representation. So, for a node U in the search space tree, we denote by FU the corresponding forest. So again, nodes are topologies. For a tree in the forest, we define the label of the tree to be the minimum label of its leaves, and the label of the forest is the non-singleton tree with the minimum label. And now we also denote by TU the tree for which the label of the forest is equal to the label of this tree. Okay, now we define the search space tree as follows. So the nodes are the nodes of the graph, and a node V is a parent of a node U if the forest FV is obtained from FU by deleting the root of TU. So I guess this is not so clear, but it will be clear now, I hope. So let's look at this node. So it has, this is the forest, it has two trees. This tree has a label 1 because the minimum label is 1, label 3 because the minimum label is 3. The label of the forest is the non-singleton tree with the minimum label, which is 1. So this is, if this is U, then this is FU, this entire forest, and this is TU. So now, if we delete the root of TU, we will be getting this node, and not this node. And this is why in our search space tree, by definition, it's look like this. Okay. Okay. So this definition gives us an implicit give us a characterization for the parents of a node in the tree. But we want, in order to perform a top-down traversal, we'll need another characterization. We need a characterization for the children of a node, so we know how to develop the search space tree. This will be given by the following lemma. So in this lemma, we show that a node U is a child of a node V, if and only if the corresponding forest FU is obtained from FV by merging any two trees. We assume that the label of T1 is smaller than the label of TU, and either the first rule states that T1 is equal to TV. And the second rule states that T1 is a singleton with smaller labels than TV. So again, I'm not sure if it's clear, but I hope it will be clear now. So now we'll show how this tree is developed. So again, in the first level, it's just and choose two different children. Now we'll look at this node. So using the first rule, so the label of the forest, the label of the tree is 1. The label of the forest is also 1. If we call this node V, then TV equal to 1. So using the first rule, we need to merge T1 with any other tree. So we can merge with 3 and we can merge with 4. Using the second rule, we will need to merge a singleton tree with smaller labels than the label of the tree. But there is no such singleton. Therefore, we can only use the first rule here. So how do we get, so we don't get this node. Why? Because this node will come only from this node. So here we can use rule number 2. The singleton with label 1 is smaller labels than the label of the forest. We can merge it with the node with label 2 and get this node. So now we can develop the tree in a top-down, from top down. In this slide, I will outline the complexity of the search space tree. So we denote by, well, I'll not get into these definitions because it might be a bit too complicated, and the proofs are very complicated. So all these lemmas leads to theorem 3, where we show that the assignment operation complexity is as the same order as the number of phylogenies. So any algorithm for maximum parsimony that in the worst case must enumerate all phylogenies will not improve our results. So lastly, I want to summarize that in this we studied the classical problem of maximum parsimony, focusing on the running time complexity of various algorithms for the problem. So we looked at all the known, not much about exact algorithm for maximum parsimony, and we looked at the running time, which has not been done before. The first approach, Cavalli-Sforza and Edwards, basically what they did is to survey the different models in a statistical fashion. Their approach yields a complexity of n-1 times the number of phylogeny. The second approach of Hendy and Per we analyzed was not, they did not manage to analyze its worst case running time. We showed it's actually faster than the ones of the previous algorithm of Cavalli-Sforza and Edwards by a factor of square root of n. And we also proposed our algorithm, which is faster than the two of them, and has an assignment operation complexity as in the same order of the number of phylogenies. So 2n-3 double factorial, exactly. And okay, this is it. Thank you.